Enlightened Illumination Techniques, presented to you by Smart Vision Lights. This webinar will be recorded, and an email with a link to the recording will be sent to you within the next 24 hours. If you have any questions on the presentation material, you may submit them via the panel on the right, and they will be answered as time permits. You will also be able to contact the speakers directly after the webinar. My name is Kathleen Straight, and our presenters today are Casey Seagraves and Matt Pinter from Smart Vision Lights. Casey Seagraves is the Business Development and Marketing Manager for Smart Vision Lights. He is responsible for increasing product and brand awareness through strategic marketing and advertising activities. He's also responsible to lead and oversee the development and growth of profitable new business while maintaining effective and key relationships. Casey graduated from Western Michigan University and received his bachelor's in business administration while majoring in marketing in the spring of 2003. He has been with Smart Vision Lights since February of 2008. Our second speaker is Matt Pinter, who has been working in the area of machine vision since 1994. As a design engineer and co-founder of Smart Vision Lights, he has led the development of the company's world-class LED lighting. Prior to forming Smart Vision Lights, he founded Spectrum Illumination and oversaw the design and engineering of lights from 1999 through 2006. Matt spent his first 7 years after college as a product manager for cameras, lenses, and lighting, working in the distribution of vision equipment. Matt is recognized as a leader in the design and manufacture of LED lights for inspection systems, optics, and electronics for controlling LED lights. Matt received his bachelor's in electrical engineering from Northern Michigan University in 1992. Matt has tested lighting on over 1,500 vision applications for companies in all forms of industries. Okay, I think we're ready to get started with the presentation. Take it away, Casey.
First of all, thank you very much. My name is Casey Seagraves, and thank you for attending this morning live, and thank you to those who may be watching the recorded version a little later on. I'd like to start the presentation by just explaining Smart Vision Lights if you're not familiar with our company, some of our goals and advantages moving forward into the industry. Our goal is to be one of the most innovative lighting manufacturers in the industry, and we think we've done that with some of the really inventive products that we have in our full line. We also offer the industry's best and only 10-year warranty option, and this is a limited warranty for manufacturer defect-related items. And we feel very confident in our products and offer the strongest warranty in the industry. We also try to offer some of the fastest delivery times. Most of our standard products will ship within 3 business days of receiving an order. Also, all of our illumination products have an integrated driver on board of each light. That means you don't need any external components. They integrate very easily, and we have one wiring diagram for all of our products. So you'll see that very simple integration, and when everything's included in the light, it makes things really easy. We also offer customized light and engineering manufacturing assistance on a case-by-case basis, and some very, very unique and creative items have come to market through this process. We also have an in-house IEC 62471 light safety testing lab. This offers CE compliance and tests all of our products for photobiological hazard classifications, which Matt Pinter will go into depth at the second half of this presentation. The integrated LED driver inside of every one of our lights is something that we pioneered. Really what it does is it includes everything inside the light that one would need for their vision application. It's easiest and most cost-effective way to integrate illumination in a vision system. There's no external components necessary. All you'll need is a 24-volt ground power supply. You'll also need a strobe trigger signal, an NPN or PNP if you wish to strobe the light or pulse the light. And most of our products even feature a manual potentiometer and an integrated 0 to 10 volt remote analog intensity that can be used with a PLC or analog card built into the system. So the big advantage of this LED driver technology is that most of the components to function the light and operate the light, sync the light with your camera to be used in your vision application, are already going to be on hand in the vision system, and no external components are necessary to control or drive the LED illumination. So moving into applications, we'll start with some automotive-related applications. Our company is located in Muskegon, Michigan, so we see a lot of automotive-related applications that come our way due to our location in the United States. This application starts off with a machined aluminum sprocket, and the goal was to read a 2D laser-printed matrix code on an unpolished aluminum sprocket gear, and they're also using that to determine the product and the sprocket's orientation. This inspection setup utilized a Smart Vision Light's diffuse light panel in the dimensions of 190 millimeters square with red LEDs. It also utilized a bandpass 635 filter, and these are some of the working distances for not only the lens but the field of view for this application. You'll see that some of the images taken give you a very, very clear view not only of the 2D data matrix code, but also its orientation on the sprocket gear. And the reason why this application was so successful was because the diffuse light panel actually produces even illumination across an entire area, and it's soft, homogeneous illumination, very diffused, and eliminates reflection. And it offers results that are sort of similar to dome lighting, where light will come from multiple angles, and that's really what's key to reducing some reflections in this application as well as others. It's become a very popular light source for us, and you'll see that there's another application that features this light also. This application is also automotive. This is a torque converter assembly. They were looking for a 2D data matrix code on this also, and they're also looking for orientation on the part due to being able to target 3 machine nut weld flanges that are sort of polished and provide reflection. So in this application, this flat surface is going to create contrast and provide an advantage with being able to locate them. Also, the orientation tolerance is very tight at plus or minus 3 millimeters. The inspection setup actually uses the big brother to the DLP 190 by 190, which is a DLP 300 by 300, DLP standing for diffuse light panel. This is also utilizing red LEDs with a red bandpass filter. The working distances are a little larger for this because the part was a little larger, and they needed to get the proper field of view. So you'll see in this product and in this image, you'll see a bench set up on the right. You'll see our DLP light. This is the 80/20 aluminum extrusion frame side view of the light with a camera peering through the center hole. Once again, diffuse even illumination from multiple angles are going to strike the surface, and you'll see the weld nut flanges are providing a very, very nice reflection, nice contrast on this product, so very, very easy to pinpoint. And also, since light is coming from multiple angles, this 2D matrix code is actually jumping out very well. Good contrast, high readability rates, and very good results by utilizing this sort of illumination. Now, the next type of application is actually still going to be automotive, but it's going to use a different type of light source. It's actually going to utilize structured lighting. So we're actually emitting a single line along this shift lever, and the goal in this application was to also view presence or absence of the shift lever button for towing, as well as make sure that it's inserted properly and view the Z dimension. So we're looking for depth in this also, and the depth can be viewed by a break in the line. So to the camera will see a slight break in the line and an unevenness. So this is what we're looking for, and what they're looking for is a consistent break and unevenness across the entire button. And you'll see from this application that it indeed provided good, solid results, and this was a very good inspection that created very good results for this customer in repeatability. You'll also see that the inspection system utilized our SP30. This is an LED pattern generator. We can emit any 2D pattern imaginable. We've got quite a bit of standard patterns available for this light, but this is LED based. It uses mask patterns as well as internal and external optics to manipulate the pattern. This was a single line pattern, and the light was actually emitting white light. These are some of the distances and field of views. The next one's actually automotive, but it's also electrical, but these are electrical automotive connectors. The internal contacts really needed to be viewed to make sure that they were created properly and there were no types of defects with these. So you'll see in the next image here, we utilize an SA30 for this light. What this is an adjustable focus spotlight. By sliding the barrel back and forward, you can increase or decrease the even illumination of a spot. So there'll be no loss of light outside of the area. It'll be a nice tight focused spotlight. We utilize the red unit for this with a red bandpass filter. And you'll see in the bench setup here that the working distances were very close. Here's your electrical connector. And you'll also see that the camera was at a close working distance also. And what we were looking for in this application were these contacts. They're coming out with a nice contrast and very bright compared to the rest of the image. And you'll see that all these contacts were nice and flat and properly placed. On the next image downward, you'll see that there is an abnormality and an incorrect seating of this contact, highlighted by the red square, that is not in proper placement and therefore not a good part. The next type of automotive application is actually mirrors, rear view mirrors, side mirrors for an application. And the goal of this application is to inspect an outer seal, any surface defects, and the presence or absence of the heater icon, since these mirrors actually had a heated surface, and also a serial number inside this mirror. Obviously, the challenge with mirrors is that if your camera or anything is over top of these mirrors, you will be inspecting that reflection and not so much the actual material of the seal and the icon. So that can create a challenge. So it was actually a very, very simple technique helped to eliminate that. And the setup was actually done with two backlights. One that was directly underneath of the mirror, and then one that was directly along the side at a angle to the mirror. The top of the inspection application was enclosed with a solid material, and the camera was off-axis, completely out of the field of view that could reflect within that mirror. You'll see that there's SOBL backlights that would work great in this application to highlight not only the back of the mirror, but the side view. You'll see that just with triggering backlight number 1, which is the vertically mounted backlight, we get pretty good results on the heater icon. The serial code is not really very visible, and the gasket's sort of challenging. So the outer gasket along this mirror is not very visible. Now, just by triggering backlight number 2, we do get very, very good results for the heater icon as well as the serial number. So we were able to obtain these images and get a pass or fail high-quality image for these two. Now, in order to view the gasket, both backlights had to be on and triggered at the same time. This gave us a very, very clear view of the outer gasket. And so this was a 2-image system. So the first image had to be taken with just backlight number 2 illuminated to view the icons. And then with both, a second image was taken with backlight number 1 and number 2 on, so that we would get a nice contrast for that outer seal gasket, which provided very, very good results also. So viewing mirrors and automotive applications can be extremely difficult, but when you're utilizing the proper techniques, it can become a little more simple. Now, this is actually another sort of diffused light application for automotive. And what this customer is looking to do is inspect 360 degrees of an automotive engine piston and to look for proper ring insulation, seating, and without any motion within the system. So they couldn't rotate the piston or the product whatsoever. And what the customer did in this inspection was utilize 6 Smart Vision lights, L300 bar lights, and with red LEDs. It was also paired with a red bandpass filter. And these are some of the working distances. And you'll see what they've done here, and you'll have an actual image of the application next. But this is a nice diagram. This was actually a 6-camera system. Each camera actually had its own L300 light that was pointed towards a housing that kind of encased the entire piston. You'll see in this next slide that there are 3-camera system here with 3 illuminators on hand to inspect 180 degrees of the product. What this did was basically they created their own diffused illuminator. It's very similar to the results that you would get utilizing a DLP light. So what had happened, what the customer did was utilize these L300 linear lights, pointed them directly at a white material that still allowed illumination to pass through it and transmit through the material. It provided even soft illumination. You can see here from some of the image acquisitions that we've got nice good spacing on the rings, nice good placement, and you'll also see a bad image with poor placement. So we've got an angular ring that wasn't installed properly, and a very, very robust solution that allowed the customer to not rotate or move the product at all, but get a really nice 360-degree view and nice repeatability on the seating of those piston rings. Next is an electronic and semiconductor application. The goal of this application was actually to view the alignment and presence or absence of some adhesive pads on an electrical circuit board. They must ensure that the 7 pads are correctly applied, they're not skewed in any way, and that they're also present in the board. The setup was utilized a diffused SB75 625 light. So this is also red illumination. It's what we call a brick backlight. It offers a very, very diffused front light and can be used off axis. So the goal here was to eliminate some reflections because semiconductors and electrical components tend to have high reflectivity. But also, since the background of this circuit board was green, we used a red LED to our advantage by utilizing a color opposite on the color spectrum wheel. Will actually turn the background of this green material very, very dark. And that creates a nice good contrast for these pads because they're reflecting back white. So if we wanted to utilize the opposite technique and highlight this green background, we would want to utilize a green light for that. It would create a bright green area where all of the background is. But in this case, we didn't want that. We wanted to turn everything nice and dark. So red is the ideal wavelength to turn everything dark in the background. You'll see that we've got good on all the presence and the alignment of all these adhesive pads. And you'll see that we've got 4 fails in this unit because 4 pads are actually missing. So this was a very simple application, and by utilizing specific wavelengths of LED, the customer was able to get a very, very good contrast and made this application very simple. So wavelengths can also be a big advantage given the color and reflectivity of the objects that you're inspecting. Here's a packaging and logistics application. This one's actually labeling. It's for a pharmaceutical application. They had multiple colored pill bottles, essentially, or medication bottles, and they wanted to make sure that the label on the bottle was not skewed. It was a plus or minus 1 degree margin of error for that label. So the challenge was that with multiple colors, it became very difficult to have a single solution that would work. So the solution was actually to use a very, very small 6-inch in length LED bar light as a dark field over top of the bottle. The very, very small edge or ledge that the sticker will provide will give you a nice good contrast and a solid line right across. So that way it didn't really matter what the color of the bottles were or the color of the label was. When you create a dark field, you're eliminating any of those colors and providing a very, very good solution. And you can see here that due to the inspection, you'll see a nice white line that's highlighted from the overhead dark field linear light. So basically, there was no challenge of viewing a label. A white label on a white bottle would have been very, very challenging to front light. But since this was used in a dark field application, we're actually highlighting a high point of the label. And it's creating a very, very good contrast and a very, very simple solution. Now this application is very interesting. This is a candy cane application where this manufacturer was looking for the presence or absence of candy canes, and also the presence or absence of the proper label on top of these candy canes. Now the challenge in this application was reflectivity as well as the multiple colors that candy canes are available in. Candy canes typically most popular would be the white and red peppermint flavored candy cane, but nowadays we have everything from Lifesavers candy canes to Cinnabon candy canes and so on and so forth. So it creates a challenge because there were so many different candy canes going down this line, so many different colors, that the best solution for this application was to eliminate color. These were also packaged with complete packages with not only cellophane wrapped around each individual candy cane, but cellophane wrapped around the entire box and package. So those created two challenges for reflectivity also. So not only were we looking at multiple colors as a challenge, but a reflective plastic outer coating that was in packaging that was a challenge. So in order to meet both and the challenges of both of those and come out ahead, was to utilize infrared lighting. Now, when you utilize infrared illumination, you do eliminate color as an option and as a challenge. So by utilizing an L300 850 light, linear light with infrared illumination and wide-angle lenses at an angle of 75 degrees across these candy cane boxes, we were able to not only eliminate color as a challenge to find presence or absence of the label as well as all the candy canes in their proper locations, but also the way that infrared illumination kind of behaves is a little different from the other wavelengths in that certain materials, it's absorbed rather than reflected. And in this case, the illumination provided very, very good results, burned right through all of the plastics. The plastics were no longer a challenge for reflectivity. And you can see that it's a very, very good contrast when you're looking for the absence of a candy cane. You have a very, very dark area, as well as no label. So this provided a very robust solution and good repeatability by taking advantage of infrared and the advantages that wavelength offers. This application was quite challenging, but very, very interesting in the end result. The goal was the customer was harvesting blueberries and packaging blueberries. Now, this application was not only looking for the ripeness of the blueberry, which meant that it had to be a color application. In the blueberry world, a darker blueberry tastes very, very good, where a lighter blueberry that's under-ripened can taste a bit sour and bitter. So what they wanted to do was look at the shade and color of the blueberries, and they also wanted to make sure that there were no stems and leaves that were mixed in with those blueberries. But another more challenging issue was that the blueberries could be infested with Japanese beetles. So they also wanted to distinguish between a ripe blueberry, an unripened blueberry, and a Japanese beetle. A couple of different applications and lighting had to be used for this. White LEDs gave us a really good result, and we were able to really differentiate between the ripeness of berries. It shows some results with white, but infrared actually had the best advantage for all. And one of the key points is that the beetles absorbed all of the infrared illumination. Beetles contain no chlorophyll. Chlorophyll can take in or absorb IR from the sun and convert it to chemical energy. So basically, when you adjusted your exposure rate while utilizing infrared illumination, the beetles tended to reflect the infrared illumination while the blueberries absorbed the infrared illumination. So when adjusting your exposure rates, you could essentially burn directly through all of the blueberries, rendering them invisible to the camera, and you would only see the Japanese beetles. So very interesting that that infrared illumination with organic materials can sometimes burn through and give you quite a bit of different results and good advantages, and this was one of them. Now this application is actually for vision-guided robotics. What this is an automated system where a food container company was looking to assemble locking clips on lids. It was a manual system at first, but they wanted to have increased speed and accuracy for their production process. So what they utilized were 2 robots, 2 conveyors. One conveyor was dedicated to the movement of clips, and the next conveyor was actually dedicated to the movement of the lids. The vision-guided robotic system actually, for this, was on the cover of the December issue of Vision Systems Design, if anyone caught that issue. The inspection setup is quite complicated. Vision-guided robotics are a very, very good solution, but there's quite a bit of components available in this system. There's a clip conveyor, lid conveyor, as previously mentioned. There's a Basler scout camera that's actually going to point directly down and look for the positioning of the lid. That Basler scout camera is actually peering directly through the center of a DLP 300 by 300 light. It's a 2-robot system. Both robots are actually complete copies of one another because they're performing the same function. So basically what would happen is a lid would come down the conveyor, would be viewed by this the first camera that is peering right through the DLP 300 by 300 light. It would send back information through the system, let the robot know the placement and orientation of the lid, and the second camera was actually viewing clips. So it was looking at the positioning of the clips to relay that to the robot so it knew exactly where to pick up the clip and then place it and clip it directly onto that lid. The first camera and robot system's job was to place the first 1 or 2 clips, and then the second robot's job was to complete the remaining clips in the system. So you can see here that what we've got is downfield from this. We've got the first camera peering through our DLP light. We've got the second camera looking at the clips. And this is actually viewpoints from the system. It's actually viewing orientation of the lid, sending it back to the system, and then it also has orientation of the clips. Now, there were some clips, due to their placement, if they were piled on top of each other too much, the robot couldn't get a clear view. It would fail that clip, and it would then pass down and be rejected, and then have to be put back through the conveyor line. So you'll see here that with the application in motion, that it actually is a very efficient system. These lids were actually 3-clip lids. They also were doing 4-clip lids. In this application that you see running in the video right now, the first robot and vision system clipped the initial first clip. the second robot had to pull double duty and clip the last two on. This actually increased their production speed by approximately 100%. So essentially doubled their speed and their production output by implementing this vision system. Once again, my name is Casey Seagraves, and those were some enlightened illumination techniques and application examples that we've run across in the past, and I hope you found them informative. Actually, I'd like to pass things along to Matt Penner now to discuss IEC 62471 eye safety.
Hello, can everybody hear me? What I'd like to do is I'd just like to go over the safety of LED lights here. If anybody's got a question, they can type it in, or I will have allow you to have some questions here at the end. What I'm going to go over is the IEC standard of 62471, and with it, let's get started here. It's mainly for eye safety. There is some skin also involved in it, but it's mainly for eye safety. 62471 is a CE standard. So if you look at any kind of product that's made now that's sold internationally, you will see a CE mark on that. The CE mark, to sell into Europe, there has to be a CE mark, and you have to meet certain requirements for that. On the CE mark side of it, for LED lights, there's a new standard. I shouldn't say it's new. It came out in about 2008, where it got started. 6 was the first release of it. And it's 62471, and it guides where LEDs can fall under compliance. Before that, it was all under the 608275 was mainly under laser. And because LEDs and lasers are completely different, with an LED being a non-coherent light source. So no matter how much a LED light is focused, it's still a non-coherent light source versus a laser being coherent. Therefore, the eye safety needs to be rated different versus a laser for damaging the eye. 2009, there was an update to the testing standards, and with that, we have 62471. Now, 62471 and RP27 are very similar. Actually, RP27 is what developed into 62471. The Europeans took 62471 from the RP27. Now, the RP27 is an American standard, a North American standard that was put together, and 62471 was developed from that. So they're very similar, but RP27 is used here in the States, although in the United States, we do not have any compliancy with LED eye safety. So here, if you're selling a product in the United States, you do not need any eye safety for LEDs. I'm sure it's coming. I'm sure we're in the beginning stages of where the laser was back in the 70s, where in the beginning the laser didn't have any regulations over it, and the CDRH decided to put that along with the FDA. We're kind of in that stage now. Europe and the rest of the world has taken it a step further and had regulations with 62471. So here in the United States, we don't need any regulation on LEDs, but if we're selling lights, or if you're using lights or shipping lights on your machinery, the rest of the world does require eye safety, and depends where you're at, but Europe in particular. So RP27 and 62471 are very similar. What we have here is with the CE mark. Again, I'll go back to that real quick. If there's a CE mark, if you're going to sell anything into Europe, or you're going to ship a machine into Europe, you do need the CE on it. Under the CE right now, for LED and anything with an LED light on it, you do have to comply with 62471 and have eye safety standards. And with that, there has to be a risk group and a full report. Now, one thing about CE is it's self-regulatory. And what I mean by that is you need to be able to meet your compliancy and have your testing and documentation to back it up. So, some companies can sell without a CE, put the CE mark on it and not have that information to back it up. that is a violation, and if they get caught, then products will get barred or fined and won't allow it into Europe. But it is self-regulatory, so it is the honor system on a lot of it, and you do need to be able to produce your documentation. So some companies can put a CE mark on it and not follow it, and they're running a risk of if they get caught or if they can't produce their documentation. So anytime you'll see our lights, there is a risk group in the data sheet that explains what risk group we fall under for eye safety. And on any of our lights, there is a full report if requested on it. And the full report has the testing in the lab under compliance. The RP27, I mentioned that earlier. UL has had meetings. They're talking about that if you want your product to be under UL, you're going to have eye safety on it. It's not official yet. They haven't. UL hasn't required it, so it's still non-mandatory. So some companies are taking the step to put their lights in and verify that they're eye safe rated, but it's not mandatory yet. UL is looking at that. So again, here in the States, we do not have any regulation for LED eye safety. When we get into the eye safety, the biohazard on that, it starts to meet compliancy. You got to be able to measure from 200 nanometers to the low UV all the way through 3,000 nanometers, which would be the far infrared. You can see here that some of the things we have to test for the eye safety, there is a skin one there, but for the UV. But for eye safety, for the UV, we have to test radiance and irradiance, and then there's also the infrared there on irradiance. It goes all the way through 3,000 nanometers. So there is some skin, but mainly most of the eye damage is rated for is geared towards the eye, not towards skin damage. Exposure time. The way that a light is tested is the light's tested at a certain distance, and it gives a certain amount of output for UV through the visible light and in the infrared. And then there's weighting factors that says that you're allowed so much UV at a certain intensity for a certain amount of time. So what we come out with is we take the numbers of where a light's tested, it goes into the spreadsheet, it's weighted over the wavelengths and time, and then there's a 62471 chart that actually tells us how much time you're allowed in that. And that how much time you're allowed at that intensity goes into what group you're under, so on how safe it is. An analogy of that would be how long you go into a tanning bed for before you actually have damage or burning. So with the eye safety here, we end up with you're going to be in 3 groups. Group 1, Group 2, or Group 3. The exempt group just says that there is no damage, or it's completely safe. So there's an exempt group, and then RG1, RG2, and RG3. So the lights are tested, and then after that, you end up into what groups? Group 2 and Group 3 are where the light could use some shielding. The light would not be directed viewing, or directed viewing, or indirect viewing at a high intensity, maybe off of a reflective surface. But exempt group and Group 1 are considered safe in all aspects through the wavelengths for viewing. Group 2 and 3 again is where we run into issues. Where you have to have labeling and tell people that maybe even shielding, maybe even eye shielding on that, there could be shielding where it's shielded with a curtain from exposure. Also, it could be eye safety with safety glasses. Most safety glasses, if people are using UV light, if it's a polycarb safety glass, will block about 98% of UV down to about 350 nanometers. So your standard safety glasses out on the factory floor will block the majority of UV light and in the LED world, because most UV LEDs that are sold out there are 365 through 395 or 405 nanometer. So standard safety glasses can do a lot of help blocking or protecting when it comes to the UV. The near-infrared region is safe because most LEDs only go up to about 940 nanometers in the LED world. There are other ones, but those are rare. and 940 is the shortwave or the near infrared, and that is safe unless you get to really high levels, which would be more like a laser type of an output where the output's enough to burn through materials. So, so the infrared and the UV, a lot of safety glasses, again, will block the UV. Back to the risk groups here. If there's an LED product, there should be, and it has a UE and it has a CE mark on it, it should have a risk group somewhere in the data sheet telling you what risk it falls under. Exempt, or RG0 sometimes it's called, is there's no hazard. RG1 would be a risk group 1, RG2, and RG3. Again, RG1 is no risk if it's used in proper, and most manufacturers will give you a proper way of using it under normal circumstances. Group 2 and Group 3 are where the manufacturer will tell you what kind of a hazard it poses and also give you recommendations on how to use it. If it has to be shielded, if the operator has to have eye shielding, things along that line. Those are the 4 groups. Again, you'll see them on any light that contains a CE mark. For us, Smart Vision lights to do CE and offer 62471 eye safety, we had so many sizes and shapes of lights and so many wavelengths, it was advantageous for our company to put in a lab. And because all the lights have to be tested, each individual light at each wavelength, whether it has narrow lenses or wide lenses. So in the end, we had 500 plus lights to test, so it was easier for us to put a lab in. Some companies may test one light and then say it complies to this light and this light and this light, but in essence, to meet 62471 regulations, you have to test each light. If there's anything different with that light, a different lens, a different diffuser, or even the different wavelengths, obviously, they all have to have their own full report and testing done. So for us, we put in a lab. Go through a little bit here in the lab. Our lab has a spectroradiometric system, spectroradiometer that can measure wavelength and power. So it measures the power of the wavelength, power of the intensity coming out, and it also gives you wavelength down to a 2 nanometer resolution. So we tested it according to 62471. It's tested every 5 nanometers. So, and we test the output for, at what that LED or what that light has every 5 nanometers for intensity. There's a lot that went into the lab to be able to do this, but again, it was advantageous for us to get our own equipment and be able to test all the lights and have full reports. So if you have a machine going overseas and you have one of our lights on it and you are getting CE for your machine, we do have the full report and documentation to allow you to put the light on the machine and still abide by CE regulations. There's a lot that goes through for our lab. There's calibration, and there's all kinds of procedures. Calibration, there's testing, the equipment list, safety protocols. We actually follow an IEC standard for protocols on that. Uncertainty measurements, and then everything has to be calibrated once a year. So there's a lot that went into that. One thing that that happens is when we get all this data from testing the light, it goes into a report. The report actually has a weighting function, and for every 5 nanometers on a light, on a wavelength, it has to, we have to have the intensity of that, and it's weighted a certain way. So there are weighting functions according to the wavelength and the damage to the eye. So it all goes into a report, and you can see there under the equations there's some summing functions. So it's fairly, when we first started looking at this, it quickly got fairly complex on how to do the eye safety. There's really no meter that does a really good job, I should say, that just you put it up there and says, yeah, you're safe. You use a spectroradiometer on it, get all the output at every 5 nanometer testing wavelength, and then plug it into the formulas. Again, full reports are available. So there's a 14-page report, and in that report it has everything that was tested on that light, along with all of the functions and all the sums for all the calculations. Those are available for all the lights. You could let us know if you need that. There's a sample one on the website. So if you go to our website under our eye safety page, there's a 62471 sample report on that. The eye safety is a button on the web page. There's a lot of information in there. We do have some data sheets there that actually have information on the lab. They also have information on certification for our lab, and then again there's a sample report. So one thing that we did is we tried to put on the website a good amount of information to help you understand if you do have eye safety for inside your facility, where you've got maybe you got a group together that does safety, that what we comply with for the eye safety, or if you're shipping it overseas and need anything that has to do with CE, or if it's going anywhere outside of Europe and you want the CB scheme, which is part of the CE mark. So again, our website has a lot on under the eye safety section. If you need more information, there's sales and tech support and orders information there. Tech support for anything that has to do with the eye safety. So if you want to send information that you need, send it to tech support for anything that has to do with the eye safety, and 62471 or testing of the lights. Anybody have any questions out there?
We had a couple questions come in, Matt, that we just answered offline, but I would just remind everyone if they have questions to email or contact you or Casey.
Okay.
Okay, great, thank you. Thanks again to our presenters and to everyone that called in for this very informative webinar. I just want to remind everyone that the webinar has been recorded, and everyone will receive an email within the next 24 hours with a link to the recording. Again, if you have questions on the material, please feel free to contact the presenters directly. Thanks again, and have a great day, everyone.